A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. You ever have that moment where you're looking at a download bar for a 100 GB AI model and thinking, there has to be a better way to live? I was staring at a progress bar yesterday, and it hit me just how much we take for granted. The invisible math that's actually shrinking these files so they don't break the entire internet.
It is the unsung hero of the modern stack, Corn. Honestly, without the advancements we've seen in the last decade from things like Zstandard and LZMA2, the distribution of large language models would be a nightmare. We'd be moving data at a glacial pace. By the way, Herman Poppleberry here, and just a quick note before we dive into the weeds, today's episode is actually powered by Google Gemini 3 Flash.
Oh, nice. A little AI helping us talk about how to shrink AI. Circle of life. And today's prompt from Daniel is right in that wheelhouse. He wants us to dig into ultra-efficient compression, specifically LZMA, Zstandard, and Brotli. He's curious about how these things actually achieve those massive ratios compared to the old guard, and why we're seeing such a surge in interest now that everyone is trying to shove 70 billion parameter models onto consumer hardware.
It's a great prompt because there's so much technical nuance that gets glossed over. Most people just right-click a folder, hit compress, and hope for the best. But the difference between using a legacy tool and a modern algorithm is the difference between a minor trim and a total reconstruction of the data.
Well, before we get into the heavy math, we have to address the elephant in the room, or the tape in the room. I feel like we need a public service announcement about tar. I still see people saying I tarred the file to make it smaller. Herman, please, for the love of all that is holy, explain why that drives you crazy.
It's a fundamental misunderstanding of the plumbing. TAR stands for Tape Archive. It comes from the days when you were literally writing data to physical magnetic tapes. All TAR does is take a bunch of individual files and glue them together into one long continuous stream. It preserves your folder structure and your permissions, but it doesn't move a single bit out of place to save space. If you have a gigabyte of text files and you tar them, you still have a gigabyte of data just in one wrapper.
Right, it's like putting 10 boxes into one giant crate. The crate is easier to move, but it's not smaller than the sum of the boxes.
Wait, I promised I wouldn't say that word. You're right. The magic happens when you follow that up with a compressor. That's why you see .tar.gz. The tar utility bundles them, and then gzip the compressor goes to work on that single stream. And here's the insider tip. Compressing a tarball is actually more efficient than compressing files individually.
Because the compressor can see the patterns across the whole batch.
Precisely. If you have 100 C++ files, they probably all have the same header guards and include statements. If you compress them individually, the compressor has to learn those patterns 100 times. If you tar them first, the compressor sees that header once, remembers it, and then for the next 99 files, it just says, refer back to that first header. We call that solid compression, and it's a huge part of why modern archives are so much smaller than the sum of their parts.
Okay, so tar is the glue, GIP is the shrink wrap, but Daniel mentioned the modern trio, LZMA2, Zstandard, and Brotli. Jeep feels like the old reliable station wagon, but these others are like high-performance EVs. If I'm looking for the absolute smallest file size possible, I'm usually reaching for 7-zip, which uses LZMA or LZMA2. What is Igor Pavlov doing in that engine that makes it so much better than the standard ZIP format?
LZMA2 is basically the king of the ratio at all costs, world. The secret sauce is the dictionary size. To understand this, you have to think about how dictionary-based compression works. The algorithm reads through your data and builds a map of strings it has seen before. gzip, which uses the deflate algorithm, has a tiny sliding window or dictionary, only 32 kilobytes.
32 kilobytes? That's like trying to memorize a book, but only being able to remember the last 2 pages at any given time.
That is a perfect way to put it. If a pattern repeats 3 pages back, JIP has already forgotten it. It has to treat it as new data. LZMA2, on the other hand, can have a dictionary size of up to 1 gigabyte. It can remember a pattern it saw 800 megabytes ago. When you're compressing a massive software repository or a giant data set, that huge memory allows it to find redundancies that gzip simply cannot see.
But there's no free lunch, right? If I'm telling my computer to keep a 1 gigabyte dictionary in its head while it's crunching numbers, my RAM is gonna feel that.
Oh, it'll scream. That's why 7-zip can be so slow and resource heavy during the compression phase. It's doing an incredible amount of work to find the most optimal way to represent those patterns. It uses a variant of the LZ77 algorithm combined with something called range coding. Range coding is a form of entropy coding that's very similar to arithmetic coding. It basically compresses the description of the data down to the theoretical limit.
It's funny you mention the screaming fans, because I've definitely sat there watching 7-zip take 20 minutes to compress something that JIP would have finished in 30 seconds. But then the 7-zip file is half the size. It's a classic trade-off. You're trading CPU cycles and time today for lower bandwidth and storage costs forever.
And that brings us to Zstandard, or ZSD, which is probably the most impressive engineering feat in this space in the last 20 years. Jan Collette at Meta designed it to solve exactly the problem you just described. He wanted the compression ratios of LZMA, but the speed of JIP.
That sounds like I want a Ferrari that gets 60 miles per gallon. How do you actually pull that off?
You do it by rethinking how the entropy coding works. Zstandard uses something called finite state entropy, or FSE. Without getting too bogged down in the calculus, historically you had two choices: Huffman coding, which is fast but not very efficient, or arithmetic coding, which is very efficient but incredibly slow because it requires complex multiplications and divisions for every single bit. FSE is a taming of that math. It gives you the efficiency of arithmetic coding, but uses a state machine approach that's almost as fast as Huffman.
So it's basically a math shortcut that gets you 95% of the way to perfection with 10% of the effort.
That's the core of it. And Zstandard is incredibly flexible. It has compression levels from 1 to 22. At level 1, it's faster than gzip and usually compresses better. At level 22, it starts to rival LZMA for size, though it slows down significantly. It's become the gold standard for things like real-time log compression or distributing Linux packages because it's so versatile.
I've noticed a lot of the AI crowd moving towards ZSD for model weights. When you're shipping a safe and source file or a GGUF, saving even 5 or 10% on a 100 gigabyte file is massive. But I also want to ask about Brotli, because that's the third one Daniel mentioned. I usually hear about Brotli in the context of web browsers. Is it just for HTML?
It's optimized for text, specifically web content like HTML, JavaScript, and CSS. Google developed it with a very clever trick, a static dictionary. Most compressors start with a blank brain and have to learn the data as they go. Brotli comes pre-installed with a dictionary of common web strings, things like doctyphtml, or JavaScript, or Common English words.
So it doesn't have to waste space learning that the word function exists in a JavaScript file. It already knows the code for function.
Well, there I go again. It has a head start. For a small file like a website's homepage, that static dictionary makes a huge difference because the compressor doesn't have enough data to build a good dynamic dictionary on its own. In those cases, Brotli can be 20 to 30% better than gzip.
It's wild how specific these tools have become. You've got LZMA for the heavy archives, Zstandard for the all-rounder speed demon, and Brotli for the web. But let's look at the why behind this surge in interest. Daniel pointed out that AI model distribution is a huge driver. I was looking into the cold start problem in serverless AI. You know, when a cloud provider has to spin up a GPU instance and download the model weights before it can answer your prompt.
That is the bottleneck of the decade. If you're running a serverless function, the actual inference, the AI thinking, might take 2 seconds. But if it takes 30 seconds to download the model from an S3 bucket and decompress it, the user experience is terrible. This is where Zstandard is winning, because its decompression speed is lightning fast.
Right, because LZMA might give you a smaller file, but if your CPU spends 2 minutes decompressing it, you've lost all the time you saved on the download. Zstandard is designed for massive parallelism. You can decompress it across multiple CPU cores almost instantly.
And we should clarify the difference between what we're talking about, lossless compression and quantization, which is the other big buzzword in AI. When people talk about 4-bit GGUF models, they're talking about lossy compression. They're actually changing the weights of the model, rounding numbers off to save space. It's like a JPEG for AI.
Right, you're losing a bit of intelligence to gain a lot of space, but even after you quantize a model down to 4 bits, you still wrap it in something like Zstandard for the actual trip across the internet.
You have to. Even a quantized model has patterns. If you have a file full of 4-bit integers, there's still redundancy. Zstandard can shave another 10 or 15% off that already shrunken file. When you're meta and you're distributing llama models to millions of developers, that's petabytes of bandwidth saved.
I saw a report from Cloudflare recently. I think Daniel might have mentioned this too, where they found Zstandard was 42% faster than Brotli for certain types of web traffic while keeping the same compression ratio. It feels like we're seeing a bit of a format war, but one where Zstandard is slowly eating everything.
It's hard to beat the versatility. One clever feature of ZSDD that I love is dictionary training. If you have a specific type of data, let's say you're a company that stores millions of small JSON objects that all look similar, you can train Zstandard on a sample of those objects. It creates a custom dictionary that you distribute to both the sender and the receiver. Then you can compress those tiny JSON objects individually as if they were part of one giant file.
That's basically what Brotli does for the web, but Zstandard lets you do it for anything. You could have a custom dictionary for genomic data, or for financial transactions, or for specific AI weight distributions.
It's the next frontier of efficiency. In fact, there's a new standard being pushed called Compression Dictionary Transport for browsers. Imagine if your browser stored a dictionary for a specific site you visit often. When the site updates its code, the server doesn't send the new file, it just sends the delta, the tiny differences, and your browser uses its stored dictionary to reconstruct the new version. We're talking about 90% reductions in payload size for returning users.
It's like having a secret codebook between you and the server. I love that. It makes the internet feel a lot more personal and efficient. But Herman, let's talk about the downside. There's a reason gzip is still everywhere. If I'm a developer, why wouldn't I just use Zstandard for everything starting today? Is it just compatibility?
Mostly, yes. Gzip is the English language of the internet. Every browser, every operating system, every tiny embedded microcontroller understands gzip. If you use Zstandard, you have to make sure the other end has the library installed to decompress it, but that's changing fast. The Linux kernel uses Zstead now. Android uses it. Most modern browsers have added support for it in the last year or two. We're reaching the tipping point where the gzip tax, the extra money you pay for storage and bandwidth because you're using an old algorithm, is becoming harder to justify.
The gzip tax. I like that. It's like paying for a premium cable package when you only watch one channel. You're paying for bits that don't need to exist. I want to go back to the 7-zip thing for a second though. Why is it that when I use 7-zip on my laptop, it feels like the computer is about to take off? You mentioned the dictionary size, but is there more to it?
It's the match finding process. To find a pattern that repeated 500 megabytes ago, the algorithm has to do a lot of searching. It uses complex data structures like hash chains or binary trees to keep track of where different strings have appeared. Searching through those structures while you're also trying to encode the data is incredibly CPU intensive. LZMA2 improved on the original LZMA by allowing for better multi-threading, but it's still fundamentally an exhausting algorithm. It's trying to find the absolute best mathematical representation, whereas Zstandard is looking for a good enough representation that it can find quickly.
It's the difference between a master painter spending 6 months on a portrait and a high-end digital camera taking a photo in a fraction of a second. Both look great, but one is much more practical for daily use.
That's a fair analogy. And for archival storage, like if you're backing up your family photos or old project files to a cold storage drive, LZMA2 is still the winner. If it takes an hour to compress but saves you 20 gigabytes of space on a drive that's going to sit in a drawer for 5 years, that's a win. But for the living internet, speed is king.
I wonder about the future of this. We're seeing more hardware acceleration now. Intel has their Quick Assist technology, or QAT, which is basically a dedicated slice of the CPU just for compression and encryption. Does that change the game? If the hardware can do the heavy lifting, do we stop caring about the complexity of the algorithm?
It definitely shifts the math. If you have a dedicated chip that can do LZMA level compression at gzip speeds, then the software trade-offs become less relevant. But we're also seeing a move towards specialized compression for neural networks. Things like weight-only quantization, combined with entropy coding that understands the distribution of numbers in a transformer model.
Right, because weights in an AI model aren't random. They usually follow a bell curve or some other predictable distribution. If the compressor knows that, it can be even more efficient.
We're moving away from general-purpose compression and toward context-aware compression. It's why Brotli is so good at text and why the future of AI distribution will likely involve compressors that understand the structure of a neural network.
It's fascinating that as our data gets more complex, the math we use to hide that complexity has to get just as sophisticated. I mean, we're talking about algorithms that are essentially trying to solve the problem of how much information is actually in this pile of bits.
It's Claude Shannon's information theory coming to life. Every file has an entropy limit, the absolute minimum number of bits required to represent that information. We're just getting closer and closer to that limit. GSIP was a great first step, but LZMA and Zstandard are pushing us toward the theoretical edge.
Well, before we wrap up the technical deep dive, I have to ask, do you have a favorite? If you were stranded on a desert island with a 1 terabyte hard drive and one compression utility, what are you picking?
It has to be Zstandard. The sheer range of it, from ultra-fast to ultra-dense, makes it the only tool you really need. Plus, the fact that it's open source and has such a brilliant community around it means it's only going to get better. What about you, Korn? You're the one who likes to poke fun at the slow progress bars.
I think I'm a 7-zip guy at heart. There's something satisfying about seeing a file size drop by 60% and knowing that my CPU worked hard for that. It feels earned. Plus, I like the deadpan simplicity of the interface. It hasn't changed in 20 years, and it doesn't need to.
Spoken like a true sloth. You value the result, even if it takes a while to get there.
Hey, efficiency comes in many forms. Sometimes being efficient means taking the time to do it right once, so you never have to worry about it again. But let's move into some practical takeaways for the folks listening who maybe aren't building their own AI models but still want to stop paying the JIB tax.
The biggest one is simple. If you're a developer or a sysadmin still using gzip for your backups or your internal data transfers, stop. Switch to Zstandard. Most modern tools like the tar command itself now have built-in support for it. Instead of typing tar-czf, you just use the ZSD flag. You'll get faster speeds and smaller files almost instantly.
And for the average user, if you're sending a big batch of files to someone, don't just use the default compress option in Windows or macOS. Download a tool like 7-zip or NanoZip. Use LZMA2 if you're sending it over a slow connection, or Zstandard if you just want it done quickly. The difference in file size can be the difference between an email attachment bouncing or going through.
Also, keep an eye on your browser's network tab in the developer tools. If you see BR in the content encoding header, that's Brotli. If you're a web developer and you haven't enabled Brotli on your server, you're literally making your users wait longer for no reason. It's a 5-minute config change that can improve your site's performance by 20%.
I love that. It's one of those rare win-win scenarios. The server does less work, the user waits less time, and the environment benefits because we're spinning fewer disks and burning less electricity to move those bits.
It really is. And for the AI enthusiasts out there, pay attention to the compression formats used in libraries like Hugging Face's Safe Tensors. We're seeing a real push toward making models streamable, where you can start running the model while it's still decompressing in the background. That's only possible with modern, block-based compression like ZST.
It's a brave new world of tiny files. Honestly, after talking this through, I feel a lot better about that 100 gigabyte download. At least I know someone spent a lot of time making sure it wasn't 150 gigabytes.
Every bit counts, Korn. Every bit counts.
Well, I think we've squeezed about as much as we can out of this topic. Pun absolutely intended, and I'm not even sorry.
I walked right into that one.
You really did. But seriously, this has been a great deep dive. Thanks to Daniel for the prompt. It's one of those topics that's so foundational but so invisible that it's easy to overlook until you really look at the math.
It's the plumbing of the internet. And as long as people keep making bigger and bigger models, we're going to need bigger and better wrenches to keep the data flowing.
Before we sign off, huge thanks to our producer, Hilbert Flumingtop, for keeping the show running smoothly. And a big thanks to Modal for providing the GPU credits that power our research and the generation of this very script.
If you're enjoying my weird prompts, we'd love it if you could leave us a review on Apple Podcasts or Spotify. It's the single best way to help other curious nerds find the show.
You could also find us at myweirdprompts.com for our full archive and the RSS feed. We've got over 1,800 episodes in there, so if you're looking for a deep dive on anything from file systems to cassette tapes, we've probably covered it.
This has been My Weird Prompts. We'll be back next time with another deep dive into whatever's on Daniel's mind.
Stay curious, and maybe try 7-zip today. Your hard drive will thank you.
Goodbye, everyone.
See ya. This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from slow